And our next speaker is a key member of the research and study team and will outline the findings of the study. The standards specifically to be addressed include NFPA 61, prevention of fire and dust explosions, NFPA 68, explosion protection by deflagration venting, NFPA 69, explosion prevention systems, and NFPA 654, prevention of fire and dust explosion for manufacturing, processing, and handling of combustible dust. David Olheiser is a senior mechanical engineer and principal with VAA of Plymouth, Minnesota. He is responsible for proposal writing, contract development, project management, and document preparation, as well as mechanical design for commercial industrial facilities. Dave is a 1997 mechanical engineering graduate from the University of Minnesota and with a professional engineer license in Minnesota and Oregon. He is past chairman of the Minnesota chapter of Jeeps and belongs to the Pacific Northwest Grain and Feed Association, where he has worked on major projects for Cargill, Columbia Grain, the Port of Portland, and the Port of Vancouver, British Columbia. Prior to joining VAA, Dave managed projects and operations for Cargill in Minneapolis and has also contributed to a wide variety of engineering projects for Cargill, Potlatch, and Purdue Farms. His work is concentrated on grain process design, environmental controls, gear drives, conveyors, manufacturing, HVAC design, and automation and equipment quality control. Please welcome Dave Olheiser.
Thank you, Jess. I will try to make this topic as exciting as I possibly can. Jim did a great job of going through the new standards that'll affect some of the things that I'm going to be talking about as well. I'm glad to hear some of the things that are in the 652 that'll talk about some of the things that we're going to talk about here. What we were commissioned specifically to do is look at how the current standards would affect bin venting today. So it doesn't take into account any of the new things or any possible changes that would happen in the standards going forward. I'm going to give you a quick summary of what we found, what we found through the study. I'm going to give you some little bit of the nitty-gritty details, calculations, and things that we went through. And then, again, I'll give you some more summary information at the end. Basically, the question we were asked to look at is what would happen if the current standards were enforced to new and existing grain storage today. We looked at a couple different scenarios with concrete and steel storage. I'll give you some specific details of what that looked like in a few minutes. But basically what we found is that you would lose a significant amount of capacity in your concrete structures. It would greatly increase the cost for new construction with concrete bins. It would change the way some of the construction would happen. Especially when you look at like six-pack configurations and the way we do construction today. Some of the things we do today you can't really do, like interior bins, interstice bins. There's no way to vent those to the outside, so you couldn't use those anymore. We're looking at about a 15% loss in your corner bins. That would be for the addition of venting, basically, and 30% loss in your center bins for addition of venting. Standalone bins, we're only looking at about a 5% loss, and again, I'll get into some more details showing you exactly what that looks like. Steel construction, oh wait, I'm still on concrete, hold on one second here. We were adding about 3 to 5% to add venting to the sidewalls. This is an increase in cost of construction, and about a 10 to 20% increase to add explosion venting in the roof with enclosures. I wanted to explain enclosures a little bit. In order to do venting, those vents have to be clear of any obstructions. If we were to look at venting in the roof, which I think some people have brought up before, we'd have to provide some type of an enclosure over there so you don't have snow and ice loading on the vents. Those vents have to be free and clear at all times. So that's why we'd have a bigger cost to add them to the roof. So it was more economical to look at the sidewall venting than it was to look at the roof enclosures. We did not look at cost associated with venting in existing silos. There's some other design considerations that I'll talk about a little bit as we get into the silo designs and how we had to add venting to new construction. And we didn't just have the time or capabilities to look at existing construction and what it would take to make those modifications to existing structures. Steel bins, again, a significant loss of capacity the way the steel bins are constructed today. Again, I'll talk a little bit about some changes we could make to how steel bins are constructed that might help with that. But again, we're looking at about a 13 to 17% loss in capacity for a standalone steel bin. I'll open it up. I mean, if anybody's got specific questions, please interrupt me as we go along, and I'll try to hit the highlights here. So, the increase in manufacturing costs. Steel bins are kind of your cheap, storage options. We're looking at about a 250 to 400% increase in manufacturing costs to steel bins to add explosion venting to it. I'll get into some details, and you'll see where that's coming from. It's a huge number, and I'll show you why. And again, we did not analyze looking at existing steel bins, because again, there's some specific changes that would have to be made to steel bins to add explosion venting to them. Here's the standards. Jess mentioned these already, so I won't dwell there. Here is the types of bins that we use for the study. We had to limit it to a certain number of bins because obviously there's a great number of bins, different configurations out there. So these are the bins we limited the study that we thought were a typical cross-section of what's used in the industry today. Concrete bins of varying size from 30 to 80 foot diameter, and then we're looking at 140 foot tall. Now 140 foot tall is a little bit larger than maybe your standard construction. I think a lot of slip heights are more in the 120 foot range. There are some 150 foot ranges out there. But we picked this height kind of in the middle. Again, that allows us to put the venting in the bins, and again, you'll see how we did that later on here. Steel construction, again, we tried to pick a cross-section of what is typically out there today, and then a pretty tall eave height. There are some restrictions on eave heights depending on if you're in a seismic region or other things like that, but this is a pretty typical eave height for what we've seen in the industry. So. Here's some specifics on the calculations that go into this. This is not the entire calculations that go into it. Jess has assured me that the report will be open for publish at some later date, so that you can read through the entire report. There is example calculations in there, and all the details that you want to get to. But I want to talk about some specific factors because you'll see how they affect the venting again as we go forward. L over D is basically your diameter and your height of your bin, and that affects really affects the flow of gases and explosion inside of a bin. Volume, your effective volume inside of a bin is basically the interior of the bin. When you're looking at a cylindrical or round structure, it's basically just the volume. But when you look at specialty structures like a square bin or something else, or a bag house or something like those sites, you have to look at an effective volume because it's not a round structure, and it affects how an explosion or something would be inside that bin. Again, and that's the same with the area, the effective area. On a round or cylindrical structure, that's basically it's your interior area. That's your walls, your roof, your floor. That's just the interior area of the bin. If you're looking at a square or a different shaped structure, that's going to look a little different because you have to take into account corners and other things. AV naught is your minimum vent area for your L over D less than 2. This should be your short squat bins. This does not come into play in anything that we're doing here with the study. Everything we have has got an L over D greater than 2 but less than 6. And that's what you see at the bottom. When we get into an L over D greater than 6, there are some more special considerations, but then you're talking a very long, thin structure. And it starts acting like a pipe. And so there's some additional considerations when you do it like that. One example is that would be like a bucket elevator. A bucket elevator's L over D is much greater than that, and you can see that different venting considerations have to be in place for that, and venting has to be along the way, and that's why they have vents every 20 feet in a bucket elevator, so that it relieves as the explosion goes through the piece of equipment. And a bin, we don't have the same issues. We can vent it in a single area. The P stat is basically your the vent relief pressure. What we use for the study is 1 psi, and that's the vents we used for here. Your KST is basically the, excuse me, I'm just going to flip ahead here. It's basically your maximum rise in pressure. It's basically how quickly your product burns. Your grain dust, your corn dust, wheat dust, that's how it burns. Volume of the bin, P max is the maximum pressure that you can get with a particular dust. I'll show you again the values we use and how we come up with those. P red is your design pressure. It's basically what pressure the vessel can stand in an explosion. You look at a concrete bin, it can hold a certain amount of pressure before there's any damage to the bin. Again, if you look at a steel bin, it can withstand a certain amount of pressure before there's any damage to the steel bin. And we'll look at some ways that we can change that in the design process so that we've increased those pressures a little bit, which lowers your vent area. And then for the L over D, then we had to add a little extra factor in there because we're dealing with a larger bin. If you want specifics again on these calculations, they're in the report, and I'll give you some details on that. I want to spend a little bit of time here on the KST and P max. These are the published values that Jim mentioned from the 61. We stuck, most of our calculations are based on wheat, which has the highest values and will give you your highest vent areas. The KST is 112, it's basically giving your burn rate. Your P max is 9.3. That's the maximum pressure rise that you'll see inside that vessel. We've also looked at specific testing you can do to get for the specific dust that you're dealing with. And that's a recommendation by the NFPA and some other standards to do that, to look at the specific dust you're using. And you can see how it affects the vent area when you're looking at different dust. And again, certain things aren't published, and you may want to. It's affected by moisture as well. So if you have a high moisture dust, it's going to have some lower values in there. So if you're handling one specific product and that's the only product you're handling, you may want your dust tested so you know exactly what your KST and your P max is, and that'll help you determine the vent area that's required. And how you would do that is they actually have some different test facilities around the country where you can actually send your dust and have it tested. And they will give you the KST and the P max for the specific dust or product that you're handling. You can go ahead and play on that if you want. They basically put your dust in a vessel and then ignite it. And they have tests. You might have to hit it again. I was having a little issue with this video before to get it to run. Try it one more time, maybe it'll go. But they basically have instrumentation inside this test vessel that'll give you the burn rate and the P max. It's kind of a large video and it's having trouble playing there, but basically it'll give you your KST and your P max, and it'll give you the specific dust that you're using at your facility. When you get into, we'll talk a little bit about the European standard that we did a comparison with. And they don't actually have any published values, and we use the values from the NFPA when we did our calculations. But again, they recommend that you get your dust tested, know exactly what your KST, your P max values are, and design accordingly. Do you want to try it one more time, or should we skip along? Let's just go ahead and we'll skip it. There's a nice fireball that blows out of there. You'll just have to believe me on that one. So here's one example of the calculations we did. 60-foot diameter concrete silo. We required 2,136 square feet of venting on a 60-foot diameter silo. This is where we get into some of the specific design considerations we looked at for reinforced concrete. When you get into actually adding vents to a silo, we needed space between the vents for actual structure, and we also needed framing to attach the vents to. One thing that we looked at additional reinforcement of concrete silos so that we could raise that P red value. By adding some additional reinforcing and looking at, adding, additional concrete to the silo, we could raise that P red value, and that would lower the amount of vent area that was required. And we did the same thing on the steel bins. We looked at a 60-foot diameter steel bin, and this was the vent area that was required. And then we looked at increasing the sheet thickness on those steel bins so we could raise that P-red value a little bit and reduce the vent area. Obviously, there's probably some, there's some contractors in the room, and there's some bin suppliers in the room, and they understand what that means to cost. And so you can see where some of that huge values in the dollar figures come from. Also, when we put venting in a concrete bin or a steel bin, we've got to have a frame to attach all that stuff to. These are the vents that we use for our study. There's a variety of different size vents out in the industry. This seemed to be the most economical one because it fit in like a 2-sheet on a steel bin or a standard size on a concrete silo. You can see the cost per vent here is quite high. Obviously, this cost is based on ordering about 3 to 5 vents. It's a little different when you buy 100 vents for a concrete bin. There's testing involved with the vents. The vents have to be certified, and they have to relieve at a certain pressure. So it's really costly for the vent manufacturers to build these vents and sell them. But when we're ordering in large quantity, I think that cost could come down significantly, so it would reduce some of the cost impact that we have in the study. Here shows a typical installation in a 30-foot diameter concrete bin. You can see we've added some additional height to the bin to accommodate the vents and some framing. I don't know if you can see all that in there. The slide's a little small, but you can also see that the concrete that has to go up in between the vent panels to support that structure in the roof, and then all the other things we have in there. Additionally, you're going to need a method to be sure that you don't ever get grain up on your actual vents. A vent won't function if it's got grain or dust or anything else built up on it. So we've shown in this particular slide, we've shown like an overflow slot. So basically, if you filled that grain bin up to the top, you would then start spilling grain out the top before you ever got onto your vent panels. Here's a typical steel bin installation. And again, we had to look at frames to be supplied in the upper portion of a steel bin with the vent installed in there. Again, you need a slot in there so you can't get grain up on your vent panel. And it would require a lot of extra manufacturing costs to supply those frames and everything in there. So here's I was talking a little bit about the 6-pack configuration, something that's pretty typical in the industry for grain storage. You would lose the interstice bins in the center because there's no way to vent those to the outside. You can see in the center bins, we've added the vents only to the open area that's exposed to the outside. And on the corner bins, we've added vents all the way around to where it's exposed to the outside as well. So you can see where we're limited by the area that we can actually install vents in, and that's why we lose a little bit more capacity in the 6-pack configuration. So all of a sudden now we're shifting back, and you might have to look at a standalone bin if this was required, because it's going to be more cost effective than trying to install these vents and losing this much space in this type of configuration. We also took a look at the European vent standard, just as a comparison to what we're doing here, and we came up with very similar numbers. We used a 30-foot diameter concrete silo, 140-foot tall, and again, like I mentioned before, they don't have published values for the KST and P max, so we used the ones from the NFPA and did calculations similar and came up with very similar results. As far as I know, the European standard is not being enforced on new construction. So they're in a similar situation that we are here in the United States. If they were to install it, obviously there'd be more cost and things associated. So it's something that we'll get into a little bit more details on, maybe what we can do to make this more reasonable within the industry. And I think some of the things that Jim talked about with the 652 will help address that as well. Major economic impact. This was kind of the main focus of the study is, okay, so if we had to actually install these vents in all new construction, what would it do to the industry? I mean, what would it do to the manufacturing cost? What would it do to the installation cost? Obviously, the vent manufacturers would be very happy. They would get to sell a lot of vents, a lot of vent panels. We estimated that it would be about $181 million in additional construction costs for concrete bins. That's based on about 92 million bushels of new concrete storage per year. And we took those numbers from an average increase of how much storage is being built every year in the United States. And this is the additional, we worked with a contractor to actually come up with these numbers and what it would take for the extra slip height, the additional reinforcing of the concrete, the cost of the vents, the cost of the framing, and all the additional labor that would go to install all that stuff. For steel construction, we're looking at about an extra $1 billion a year in the United States. This is based on 1.6 billion bushels of new concrete storage, or new steel storage being built every year. Again, that's additional steel costs for the bins themselves, additional costs for the metal framings for the vents to be installed in, additional costs for the vents themselves, and some loss. There's some lost capacity there as well that we figured into those calculations. So. Other possible design impacts we've talked about: the 6-pack configuration loss. I mean, it's a bin configuration that's used in the industry, and some of those losses would be felt. Additional costly reinforcement concrete bins, stronger steel sidewalls. One thing we didn't talk about is flat storage buildings. The NFPA doesn't really address flat storage buildings and how those would be vented specifically, so that we didn't really look at that in this study. So what's next? And that's kind of we've talked to the NGPA about, what's next and how, where do we go from here? Are these new standards going to be enforced on new construction? I haven't got a feel from the NFPA yet if that's, something that's in the works or not. Some of the things that, as Jim mentioned, now that we're in a public comment period, hopefully some of these things will be taken into account. We'd like to look at, it's our feeling that if the NFPA were to look at like partial volumes of bins, instead of looking at the whole volume of bin, maybe that vent area could be reduced. That basically represents that the whole volume of the bin is not going to explode at one time. It is never at the same point that the entire volume of the bin has reached an explosive level. That's also, I mentioned in here about talking about the lower explosion limit. There are devices out there that can actually measure when the dust gets to that explosion limit, and we could look at how that affects partial volumes and when an explosion is actually potentially has the potential to happen. And then Jim also mentioned potential isolation scenarios. How can you isolate one bin from the next? How can you isolate equipment? How can you isolate different things so that we can reduce the explosion potential? We'd also like to look at guidelines or recommendations for modification to existing structures. What are we going to do with all the existing structures that are out there today? The concrete bins, steel bins, different things. How do we add vent panels to a concrete bin, and what can we do to reduce the risk to structures and other things? There's nothing in the guidelines that addresses that. It basically says, here's what you need to do, but doesn't do anything for existing structures. If we had to go and cut in holes and add panels, we would lose a significant amount of capacity and a huge cost to do that. I guess we're going to take questions at the end, but I don't know if you want to, we'll go from there. I'll leave a little time for Jess to go through his material. So.